Hello, this is Byron, and I'm going to be talking to you about Learning Goal 1.3. I understand how images are formed and how scientists use images to study nature. This has a bunch of sort of subtopics, and we're going to go through them one by one. First of all, I understand that I can see objects or images of objects because of the light rays that they emit or reflect. And I understand rays, light rays, as a model for light traveling in straight lines. I say that because we're going to later in the course start thinking about light in different ways. The second subpoint is I can describe the difference between specular and diffuse reflection. We'll define those. I can understand and discriminate between real and virtual images, and we're going to define those as well. And I can use primary ray tracing techniques with pinhole, mirror, and lens systems to predict the position, magnification, the type, meaning virtual or real, and the orientation of the images. And I just popped in for fun two pictures from the Book of Optics by Al-Haytham, and we're going to be talking about him a little bit in class as well. The first thing that I want to look at is this idea that light is traveling in straight lines, and they're emitted by shiny objects like the sun or a light bulb, or in this case, a candle. And you can see the rays is traveling outward. And one way that this can be somewhat difficult is that the rays are going in every direction at once. And if we show them all, it would just be a mess on the screen. So we have to show some of them. We have to choose some of them to show. So from the top of the candle, you can see two rays coming out, but remember there's rays going in every direction. And from the bottom of the candle flame, we see two rays going out as well. Now imagine that rays are emitted from every point on that candle in every direction, but there's just no way that we could represent that around the candle flame. And you'll notice two objects on the table next to the candle. They're going to be important in a little bit. One is some apples and the other is a mirror. Now, when we look at the situation and we put the mirror in the right spot, we can see an image of the candle in the mirror, the candle flame. So we see it looks like it's upside down, but you can see it there at the bottom. But we don't see an image of the candle in the apples. And this is going to get at an important point that we're going to talk about in a sec. When light hits the apples, they bounce off in every direction, and then new rays appear, and those rays go in every direction, and some of those rays come to our eyes. So the reason we see things in this model is that light rays travel to us from objects that have reflected them, and that those light rays ultimately started at an emissive object like a candle flame or the sun or a light bulb or something that emits light. So we see the apples not because they are emitting light, but because they are reflecting candlelight. Likewise, when we see images in a mirror, the light is also reflecting off. And you might say, wow, so in a mirror, light bounces off, and in an apple, light bounces off. So why don't all apples look like mirrors, and why don't all mirrors look like apples? Like, what's the difference between a mirror and an apple if they're both just reflecting emitted light? So what we need to do is understand the difference between specular and diffuse reflection. So I've shown here a candle, and you can see light rays coming from every part of it, going to every part of that screen. And again, we haven't showed all of them, we've just shown some of them. And they bounce off the screen, and then we see the screen because those light rays have bounced off and come to our eyes. But we don't see, it's not a mirror, it's just a cardboard screen, let's say. Now, if you looked really close up at that cardboard screen, you would notice that the surface is rough. And the light rays, even though they might all come in at the same angle, all bounce off at totally different angles because of the roughness of the surface. So really, the difference between specular and diffuse reflection has to do with how organized the reflections are due to it being a sort of chaotic surface versus being a very flat surface. So when light rays bounce off a mirror, they bounce off in a very uniform way. You know, one of the ways you can make a mirror is take glass, which is very flat, and then apply a very thin layer of metal, which is good at reflecting light. And the flatness plus the good at reflecting light makes a nice mirror. And so the difference between specular reflection, which is when light bounces off in a really uniform way, like in a mirror, versus diffuse reflection when it bounces off in a very chaotic way, is shown here. Now, when you place a candle in front of a piece of cardboard and you get diffuse reflection, you don't get an image. You don't see the candle there. If it were a mirror, you would see an image, right? And so we need to understand what we mean by the word image. So if you were to drill a hole in that piece of cardboard and let some of the light through. And you make it a small enough hole so that only certain rays can pass through. Now remember that the top of the candle at left was shining rays in every old direction, but only one made it through that hole. Likewise, the bottom of the candle flame was shining rays in every direction, but only one made it through. And those impacted a second piece of paper here in the back. And when they impacted it, they bounced off that paper and formed an image. And again, here you see diffuse reflection. It's bouncing off in every old direction. And that's what you would want, so you can actually see the image form there. So this image formed in actual physical space. We could put a piece of paper there or a piece of film there and actually record the image, actually see it there. And that's what we call a real image. Now in a virtual image, a totally different type of thing, the light rays don't actually meet. So here's an example of a candle flame and light coming from the tip of the candle flame, bouncing off a mirror, and this is specular reflection, and bouncing to the eye. No light actually passes to the right-hand side of the mirror. There's probably, if this is a wall mirror, there's probably another room over there, or at least the interior of the wall. But when we see the rays bounce off the mirror, we project them mentally backward to a point in space. If you project rays backwards mentally to a point in space and imagine the image as being there, then that's what's called a virtual image if that place is not in real physical space, if the actual light rays don't actually meet and cross at that point. You could never capture, when you look at yourself in the mirror in the bathroom, you could never capture that image on film. Now you could take a picture of yourself in the mirror, that's a different issue, but you can't actually get behind the mirror and actually put a piece of paper or film where the candle appears to be because you physically can't get there. The light rays aren't actually going back there, it's sort of an optical illusion. So virtual images are sort of mentally projected images as opposed to real images which you can actually form in space. Now, I've shown you pinholes and I've shown you mirrors, and what we're now going to do is get into the more complicated question of how we create images using lenses and curved mirrors. One of the first things we need to learn about is the principle of refraction, this idea that the light, when it transfers from one medium to another, the rays change direction. So for instance, here's a picture of a fish and light rays from the fish. Of course, these are probably reflected from some light source, so we're omitting that part where the light emission happened from the sun or the moon. But light rays are now reflecting off the top of the fish, passing up to the surface of the water, and then they're bending at the surface of the water. And that's something we've talked about in class, is the idea that light bends, the light rays bend when they travel from one medium to another. Now, we project that fish backwards in space and actually think of the light rays as meeting somewhere else. And so here, looking into the water, we've created a virtual image of the fish, and it's not at the location where the fish is, and the light rays don't really meet there. So we've created a virtual image. You probably noticed this. This is why if they're standing in the water, their legs look short. Their feet look higher up than they would be normally. Now, if you pass a light ray through a triangular piece of glass, and this is glass water, both of them bend light, the light rays pass through and they change direction. Now, different shapes of glass have the light pass through in different directions. So if you shape a piece of glass just right, with higher angles at the top and lower angles at the bottom, you could actually have all the light rays come in, meet at a point called the focal point. And so a curved lens, this is a lens, a piece of glass, like an eyeglass lens, but it's seen in cross section. So we're looking at it as if it were cut through the middle. All the light that comes in goes to a focal point. Now this is very different than a pinhole. Remember, in a pinhole, only the light that happens to pass through that tiny little hole can be sent to the image. Now we can actually capture all the light that passes into the size of the lens, which could be rather large, and send it all to one place. So this is an exciting development in the history of optics. Now, some lenses have virtual focal points. These are concave lenses, and the light rays, since they bend outwards, only appear to emerge from a virtual location in space. Mirrors can also create focal points. A curved mirror, in this case a concave curved mirror, can send all light that's incident on it into certain locations. And a convex mirror does the same thing as a concave lens. The light rays all sort of spread out and only appear to come from a specific point in space. Now you might think, oh, the image must form at the focal point, but actually that's not true. And this is where we get into what's called primary ray tracing techniques. Here is a lens seen in cross-section, and you can see that there's a center C of the lens, and there's two focal points on each side, F, and that's because light could go through either direction. We're going to have the light come in from the left-hand side. And there the light is emitted from the top of the candle flame, and three rays all coming from the top of the candle flame. Remember, they're going in every direction, but in this case, we're going to have them go in these three directions because we're just choosing three, what we're calling the primary rays. The first of the primary rays goes straight parallel to the geometric center of this system, what's called the primary axis, and it hits the lens and it bends and it passes essentially through the focal point. A second ray passes through the center of the lens, and a third ray passes through the nearby focal point and then bends into a direction parallel to the optic axis. All three of these rays meet at a point, and that's where the image of the candle flame will appear. Not at the focus of the lens, but at another location, which we call the position of the image. So we can actually trace out what it would look like if you were to look at a candle flame through a lens. Here you see rays in gray coming from the top of the flame, and you see rays in red coming from the bottom of the candle. And you can trace out where these will all meet, and they're bending at the right angle that they need to as they pass through the lens. And you can see that, of course, if your eye was looking through the lens, you would see the red rays and the gray rays as they appear at the very right-hand side of the system. And you would see the candle flame appearing to sort of float right in front of your eye, and the light rays are diverging from those points, much like as if the candle was actually sitting right there. This is a real image. You could actually capture it on paper, and you can also just look at it floating in space. And if you move your eye side to side and try to figure out through sort of this idea of parallax, where is it in space? You know, if you close one eye and close the other, things jog back and forth depending on how close they are to you. The candle will actually appear to be as close as shown in this image of the candle, and not like it's all the way back behind the lens. It's a really neat phenomenon that you should check out in the lab. If you look through a concave lens, again, we send primary rays, one passing through the center of the lens, one passing parallel to the optic axis, and now, because it diverges outward, it moves outward from the focal point, so in a point aligned with the focal point. And if we trace those rays backwards, we see a tiny little virtual image of the candle flame. And that's why when you look through a concave lens, the candle flame looks very, very small on the other side. Here we see that we can create real images using concave mirrors. So this is if you have sort of a cup-shaped mirror and you hold a candle in it and you look at it, you can actually see an inverted or upside down, that's the orientation of the image, inverted, upside down little image of the candle. Now in this case, the magnification of this candle is about, what do you think, 80%, 70%? It's smaller than the original. And you measure the magnification by just measuring the height of each of the actual object, the candle, and also the size of the image as well. Here we see a convex mirror, and the light is bouncing off of it, and the light appears to be originating at a point behind the mirror. This is an example of a virtual image that is formed by a convex mirror.